So we tried to have like a certain gradient in terms of first giving an introduction, which was both meant for the developer, non-developer. This in the sense of mechanical sympathy, so that we all know what we want to achieve, both from a developer and from an engineering point of view. Then started over with the basic API that Alex did. Simon went into how modern C++ can make your code more readable and more efficient and also safer. And then Matthias upped this one level by saying like, okay, if you use algorithms and SIMD, that you get also like an incredible performance boost and safety reliability and also this merge API. And now the thing is like to go like say the last step to get an arch on what you should actually focus on, because I mean like if you're in the technical detail, you're very quickly getting into small scale optimization and details where you lose the big picture. So this tutorial is mostly about talking how to avoid premature optimization. I mean, we all know about it, that we should avoid it, and but I just thought like I put some slides up to press some thoughts, which I hope this is all preaching to the choir, that you all know about this, but I just wanted to set this out as a reminder to that we can iterate on this and be mindful of these things. So the agenda is basically talking a bit about, I don't know why I call it advanced techniques, because basically they're all 20, 30, 40 years old, but just mentioning we should think about like what happened before, think about the theory, signal processing. There are lots of techniques that one should gradually need. It's a bit like a toolbox. If your only tool is a hammer, all problems are nails, even if they're screws. And this is just like be mindful that this is a continuous learning. Think about algorithms, how you can simplify from the overall architecture point of view. And then how to go into unit testing. There's a running gag also with Alex where I said like, did I mention today that I love unit test? Probably once or twice per day, because this saves us. The earlier it breaks, the earlier you test non-compliancy, or if you make a modification in the code, the earlier you know about this, the quicker you can fix it and isolate it. But also there's a building block for improving cybersecurity. And I think this is like one of the next challenges for GNU Radio in order to be reliably used also in industry and critical infrastructure. We have to become tougher, more robust. And yeah, I think unit test is not the only thing, but this is one of the first steps that one has to do. Then talking a bit about benchmarking, I think the material that was compiled by Matthias is way better than what I present. So the ultimate reference on benchmarking would be what Matthias showed. And then the last thing is like how to, like a strategy, how we can go forward with respect to secure coding practices, but on a very high level. So, as a running gag, XKCD, are you premature optimizing or just taking time to do things right? If you look for a flowchart, yes, we are. This is like from Donald Knuth, premature optimization is the root of all evil, because sometimes we think what is important, we spend way too much time on optimizing the small performance in a small part of the code that has not a big significant impact in the overall program. So sometimes I invite you always like step back, think about reflecting what is actually important, look at the big picture and see what are the main bottlenecks, or how could you phrase the problem differently so that you can implement it more efficiently. So try to understand what you want to achieve and then develop the tools, not saying like, I have these tools, how can I make it all the time? I mean, like sometimes it's useful. There's maybe the difference between engineering and physics. As an engineer, you get a certain set of tools and then you're trying to find the best possible solution within a given boundaries. And like in science and research often is, okay, I just have limited tools, but how can I change the boundaries so that I get the best possible result out? And this is like the theme of also mechanical sympathy. We should strive for making algorithms that are both abstract and make sense from a high-level point of view, but that's also well implementable and corresponds to the hardware that is underlying and used to implement that. So we all love C++. if you haven't dealt with C++ before, I invite you to look at this video, C++ in 100 seconds. After that, you're a C++ programmer. That's very easy. Actually, I invite you to offline look at it. It's really easy. I was surprised and I thought, like, that's a joke. I looked at it in the center also within our C++ user group, and people say, like, yeah, if you cut everything, all the fluff away, there is not too much you need to know. The language concepts are simple, but the other one is often like engineering practices, like the fluff and the ceremonies that we put around. So if you started with that, then this has been gradually introduced by from the CPP. There was Herb Sutter and Bjarne Strustrup, sorry. Herb Sutter and Bjarne, so the two gods of the C++ standard. And Bjarne, who invented C++, and they looked at the practices of C++ over the decades and said, like, what is actually modern, how should we practice C++? Not in the sense of thou shall not or thou shall, but it's more in the sense of how can you use C++ to make your life easier? And there's some good patterns, and they're described in here. Yeah, so once you've gone through the 100 seconds, and this is a bit more than 100 seconds, but feel free to consult it every now and then. I think it's nice to read. Then you're basically all set. You don't need to know much more about C++. And I think we should also train people on C++, not from a C perspective, but right away from C++. So that's all. Any question? No, sorry. I think it's a bit more. But in a nutshell, that's the thing, is what one should learn, continuous learning and practice and iterate on that. So the general strategy: avoid premature optimization, focus first on correctness and readability. So make sure that the algorithm get your job done, that your peer and your colleague can understand it, and then also think about, like, how can you simplify your structure so that it's long-term maintainable. Because if you have a solution that gets your job done within a short amount of time, and you just need it for a year, this might not be such a big issue. But if there's some chance that this has to be maintained by a long time by the community, simplifying things goes a long way. And only optimize when it's strictly necessary. If you see, like, okay, there's a bottleneck, first try to change the architecture and maybe then do micro-optimizations. So mechanical sympathy, so align your code with how hardware works to improve the performance. And what I would like to stress is focus on the numerical complexity first. And then, to make your life easier, use the modern C++. I know that the modern is overused, because modern is always changing every couple of years, but languages, like natural languages, are evolving. There's not a static object where you say, like, I learned English in the 1600, and then everything is done. Language, like people, are evolving, ideas and paradigms are evolving, so keep up to date with what's common practice. So numerical complexity, I think the easiest example, we're not going too much into detail because it's heavily overused, is like, if you can, don't use the direct Fourier transform, but use a fast Fourier transform, obvious. But they're also in signal processing. There's like this weird trick, sometimes would that say now in YouTube for catching up lots of likes or phishing, is certain things are better to be computed in the time domain, certain things are better to be done in the Fourier domain or frequency domain. One of them is using the convolution, where you can reduce the number of multiplications, especially for the Hilbert transform. This is very good. Or the other one is median filtering. Then you can do a naive one, which has an n k log k complexity. But if you go for a sliding window, even though you have like a bit of RAM or memory overhead, the complexity goes down significantly. And then you have others like naive or Strassen matrix multiplication, time warping. I think dynamic time warping is also like at least a technique that we heavily use, where you have like a naive and a more improved version. And also for polyphase decimation filters, there are also several ways. So be mindful, learn. If you don't know them, just Google up. And it's also, for me, was very educational. And because once you do this, you get also inspired for other problems where you say like, oh, this looks a bit like this and this looks like this. Let's maybe combine these two techniques and you can get a better solution than if you just do brute force. So yeah, mechanical sympathy. You don't have to be an engineer to be a racing driver, but you do have to have mechanical sympathy. Get informed about how the machine or the architecture you're working on, how it works, what it's designed for, what it's good for, and you become much better. And this is like some of the aspects. Learn how CPU caches work, branch prediction, memory alignment. I mean, like, you don't have to do this. You don't have to know this straight away to be a good programmer. But this is, let's say, the path that most of us went. And they're very good YouTube resources to get into that. So you don't have to know this to start, but invite you while you're developing that you spend some time on, say like, oh, I don't know what does he mean with branch prediction. Can I do branch-free or log-free programming? Just Google or you look at YouTube. There are lots of good lectures on that. And they're quite, many of them are quite good. This is like how a modern CPU looks like. Important is that the designers of the hardware had a certain idea how it's supposed to be used. If you write your code which is orthogonal how it was designed, it will still work because they will try to match this impedance mismatch, but you will not get the best performance out. So if you know what the general structure is and you write your algorithm accordingly, then the likeliness that both ideas from the hardware design and the software design match is better and you get a better outcome. That's, for example, like with the cache structure. I'm not going into detail, but this is an interesting topic to think about, like how does a computer actually compute? How do data get from main memory to the L3, L2, L1 cache, and then later in the registers? They also out of order execute and then back. There's like a small slides if you want to get an intro with more links to more detailed information. And yeah, just to put into context why this is important, depending on the performance you want to achieve. If you have something that is slow, you don't have to care. But if you go in the realm of where you need a very fast throughput in the order of hundreds of megasamples or gigasamples, then things like context switches or atomic operations become significant and where you have to start counting instructions. So yeah, use modern C++. I think Simon already gave an introduction, is use algorithms over manual loops, learn a bit about move semantics because this avoids unnecessary copies. And especially for return time optimization, this is maybe a concept for many that people say like, how does it work? Does it actually work? It's useful to get into that, think about it, and then your style will also change and suddenly we'll see that suddenly the code becomes faster and faster. Yeah, maybe I should have added here the slide const expr everything. Whatever you can compute already during compile time, which doesn't change during runtime, try to make it a compile time expression, because this optimization takes you only once, but then in the runtime you benefit from it and you get much faster code. And yeah, again, C++ core guidelines are your friends. They're not rules. I mean, like, they're not rules they say you must, but there's like recommendations and good best practices, basically. Yeah, leverage the power of modern C++, wide expressive, maintainable code. And before you start doing optimizing, you should develop a certain trust into the compiler, because the compiler has a much larger scope and complexity it can optimize than humans can. Maybe in the early 90s, I'm a victim of myself. In the early 90s, I thought I was one of those guys. Now I know better how to write code. I tell the compiler, do this and exactly this, and if the compiler didn't do this, I started writing assembler code. I stopped that in the 2004, 2006 area, because then I realized that the compilers can generate faster, more efficient code than I could do within 3 months, and the compiler did it in 6 minutes. As always, like with lawyers, it depends. There are exceptions, but trust that the guys who build compilers and the standard libraries, they know what they're doing, because they're dedicated on that for decades of their life. Yeah, treat C or C++ like any modern language. It's not a fixed, unchanging construct. This involves, as more meta, continuous learning, listening to other people, and reading and practicing. It's like with any sports. You can think I'm the fastest 100-meter runners, but unless you do it, even to like an amateur level, you will not get better. So try some projects either with GNU Radio 4 or even like some just coding exercise. that helps you to become better. And for example, menu loop, we all know how to write a menu loop, it's obvious. But if you do this with an SDE algorithm, it's shorter. You don't have to read everything. I mean, in this example, you might think, oh, come on, this is just like 4 lines of code. I can understand this. But if the loop becomes larger and larger and larger, it's difficult to see what the intent is. And if you write it with a std accumulate, for example, the intent is more clear also from the compiler point of view, and the compiler can do a better optimization. I think that's most of the structures which I'm showing now is if you express your intent clearly, it helps not other people to read your code better, but it helps also the compiler to pick up on those cues and optimize much better. Pushback, this is an example. You can say like either you do like a manual copy, or you just say like, let's do a std copy. Many people think like, now this or the other version is faster. In the end, just benchmark. If you look at these different examples here with the pushback and here with the copy, you can see that for the classical loop, even though you have a fairly like O1 optimization, it generates lots of assembler code. Please don't take this that each instruction takes like 1 clock cycle. Some of them are overlapping. Matthias showed it a bit in his more detailed view. But putting small code snippets in compiler explorers gives you already an idea how complex it is from a compiler to generate a function that executes this code, or if you use a standard algorithm, you can see it's much more optimized, even on a very low optimization level. So here the compiler sees the structure and can execute a few lines of assembler, and here it's, I forgot, 100, 150 instructions, so it's definitely slower if you write it that way. Same, another example, you can express it with loops, or you can express it with algorithms or ranges. Ranges is even better because here sometimes you have this like error, potential typing error, that you begin and end are not matching, that you take this from different collections, that you begin and end is from one vector or another because you make copy-paste. So in ranges, the main benefit of that is it becomes less verbose and safer in terms of typing and debugging. And again, like an example, if you do this, that's instructions, and the other one is equivalent, if not even faster. C-style arrays are dangerous because of auto-memory reads. You can, and usually this is also unsafe because from a design point of view, because you have to give a pointer to int and the size of the array separately. So if here you get a mixed match and you have a wrong integer, so if you don't put n but another integer, that's a source of error. If you use an array as an abstraction, the size is automatically built in, and you can even write it in a way using stdspan or other iterator that this algorithm just not works with C arrays, but also with vectors and other type of collections. You can still use this form, but this is a bit better. Reinterpret cast. We all love it. We're often used to it, but in many cases it's often UB, not in this case. But there are new language features like bitcast, which are way more expressive to express if you want to, for example, just have a different representation than going back without manipulating it. But reinterpret cast, many of the uses that we have it, type punning, and it's often UB. So that's the same code before, after. UB case, for example, this is like this famous Quake 3 inverse square root example. Looks nice, looks very efficient, it's like a micro optimization, but ultimately it's unsafe. I think I put also a link on why it's unsafe, because the compiler is allowed to do out of order executions, and then some of your constraints and your assumptions that you put into the code are not valid anymore from a compiler point of view, because the big reason why many of the structures are UB is because we as humans think about like, okay, the compiler does first this, then this, then this, and then this, and this. But if there's no constraint, the compiler is free to order it in any put it in any order where it thinks it's most efficient. So the ordering of how you write code is not preserved. Since this is already since a couple of years, but this becomes more and more prevalent because we have more const expert evaluations and more optimized compilers.
Just to note to why that is, UB. And we talked about restrict before, right? The idea is that if you have two pointers and they're pointing to a different type, the compiler assumes they are not pointing to the same memory. So they cannot alias and the compiler can optimize. That is why you have that feature that reinterpret cast is full of UB. Right? So it's a good thing that you have that, it's for optimization, but then you also have to understand it does not work like you can just look at your memory and yeah, you can just do the pointer and interpret it differently. Yeah, on assembly level you can, but the language has a different abstraction level.
Yep. Yeah, and also Matthias, maybe you can explain, Eric, why this double circular buffer is UB, but please afterwards, I guess it's a longer discussion, because I couldn't make that argument. No, but it's, I'm like, we have like two resident C++ gurus, Ivan and Matthias are here, and they often told me like, yes, I know what you mean, but it's not safe. And I had to bow down and say like, yes, you're right, and I promise to improve and become better. In terms of resource management, this is maybe obvious. Try to avoid new and delete. The resource allocation is RAI, is basically the name of the game, which is much safer. And if you still need pointers, for example, wrapping some C-style array which you get from a library, rather use like a unique pointer. Some might think like by default to take shared pointer, but if take always the object of the least privilege, that's also like a security practice. Start with unique pointer and only use a shared pointer when it's absolutely necessary. And the code will generate the same or faster, and you're happy. Now, in terms of unit testing, we have adopted the Boost UT library. I mean, this is not strictly a boost. It doesn't have any further boost dependencies, but is within the realm of the ecosystem of Boost. But it's independent and depends only on the standard library. It's a C++ micro unit testing framework. It's lightweight, header only, and importantly macro-free. Because I mean, unit tests are always nice when you execute them. Also, Google tests are nice when everything runs and passes. But as soon as you get exceptions or threading issues, the line numbers and the debugging information you get are garbage because many of the macros changed the line numbers and inlining what you see. And this problem is not with the UT library testing framework. And it's also faster to compile than Catch2 or Google Test or any of the other one. Has a, to my view, like a very expressive syntax. And yeah, it's fast to compile. And here's just some examples. How do you declare a unit test is with a user-defined literal, like a test, and then you just write within this lambda your expression that you want to test. It can be asserts or can be expect. Expect has an advantage that it gives nicer compiler error outputs. With some other examples, just have a look on the documentation. It's really useful and a very good library. Now, benchmarking. There is like Google benchmarks, of course, but we thought like we didn't want to add too many cross dependencies, so we thought like why not piggyback on the same UT test library, also like a micro benchmarking facility, which uses basically the same syntax. So whenever you write a unit test, you can quickly turn it into a benchmark, and any benchmark is automatically also a unit test in the build system, where you can say like I declare a benchmark, execute whatever course you have, and then you have like certain tasks where you can basically force certain optimization that is suppressed by the compilers. And you have also possibility to put certain markers within your code where you say like I want to have a benchmark not just from the start stop but also intermediate steps. There's also like an API for that. You can have a certain benchmark to define explicitly how often it should be repeated to get a bit of statistics if it's a non-deterministic test. And also can, yeah, as I mentioned earlier, can also be used as a unit test. And produces a, I hope, reasonably nice table output, which is color-coded. You see like which test fails and how it passed. You have a certain param information which is coming from the counter interface, so it's basically the same interface as perf. So if you use perf, this is the same information as if you would put in a profile, an external profiler, and they get like a certain information, what is the mean, min, standard deviation, median, max of the individual test, how much the test totally, and then like some CPU low-level core information on how many instructions were executed, and branch misses when you see like, okay, there's a certain non-deterministic behavior in your algorithm. This is not, let's say, whatever you test, be careful what you test. It's basically a little bit like don't trust any statistics you haven't faked yourself. This is a micro benchmark. Both, I think in terms of the infrastructure, it's implemented correctly, but what you put into the unit test still has a certain bias, depending on from where to where you test and what you optimize. But I think this is a very lightweight way to get a first order of magnitude. If somebody says like, my block runs faster than yours, please write a small benchmark, and then you can see at least the first order whether it's true or not. And that's also the reason why we have this process BON and process bulk interface, because that they are very easy to integrate into these tests. Yeah, then this is like for if you have small micro tests, but sometimes you have like larger complex objects. For example, if you want to debug the scheduler itself, I mean, you could in theory instrument every block and add like a profiler and select please emit some message to some queues. And then you would have basically instrument everything over here. But what we suggest is like don't instrument the blocks, but instrument your scheduler, because then you have a better control on from where to stop, because otherwise you can risk that for very simple blocks your instrumentation is more heavy than actually what you want to measure. And there we backed on the Google Chrome facility. This is like a Google tracing, which also used in Android for the Chrome browsers. You have different interfaces. Either if you use Chrome, you can just type in Chrome/tracing, but there's also like a website, and it takes the standardized format and produces flame graphs or any other analysis that you want. And this is the same format used by Google, Android, Clang, and both for the compile and runtime analysis, and we also added as an optional output for GNU Radio 4.0. So what you can do is, yes, purpose is to do runtime profiling of the scheduler across multiple computing domains. And because we use the Google Trace format, it's easier to share, easier to analyze with common tools, so we didn't have to build up our own ecosystem on documenting. And also we don't have to do the maintenance on the secondary tools that build on top of that. So it's opinionated, but I think it's very good. Have a look at it. There's some notes on how to use this, and like a quick example is how you would typically run with that. So you provide a profiler, you have like a handler, which typically you make one handler per thread, and then you have runners where you can say like I have a handler start asynchronous event, which basically you lock this in the trace. You can say in the profiler whether it's locked to memory, to file, or to output. And then you can add like this small explicit event ends or markers in what type of code you want. And then you get like similar to the benchmark, like an output where depending on where you place them, different informations on the statistical distributions, also the cache misses and so on. And here you see a comparison between if there's a default profiler, which goes to memory, and then you can read out afterwards, the null profiler, no profiler, and the overhead in this example, which is very tight loop, is reasonably minimal. So this is normally this, yeah, if you put it out, then it's close to nothing. It's like 14% for a loop that you normally wouldn't instrument like this. So how does it work? You have a thread handler that where you get a handler from the profiler, and then you have the API for measuring a complete event, where you select handler start complete event. Here are the names that are being put into the history buffer. And then either by explicitly calling event finish, you say that's the stop mark, but because it's RAII, if you leave it out, then it basically measures until it runs out of the context. So this is optional. So you say either instrument the whole method, then you just have to add one line. or you say, I just want to have it until this point. And the nice thing is, the handler, you can write it in, but because we have the null implementation, it's compiled away. So that's for debugging, you leave it in, and for production code, you just say, like, provide another profile implementation, and then you don't pay for what you don't need and use. But it requires a recompile. It's not a runtime decision. Or you could make it a runtime decision, but the ones that we implemented are compile time so that we can guarantee this profiling adds no overhead. Then you can do a similar API for asynchronous events and also for instant events when you just select, I want to log here.
By the way, I mean, for profiling, this actually makes a lot of sense to compile it out, but this also belongs in the category of do not do premature optimization. When I was doing the logging framework, I was optimizing for, like, can I compile out the whole thing? So I needed to have, like, macros, because I can if-def them away, right? Don't do that. Like, if you do something in a hot loop, then the single branch that you're not taking, not a single time, your pipeline will be happy about that bubble state. Fair, don't worry.
Yeah, and my recommendation is do not instrument the blocks themselves, but if you do an instrumentation, do it around the blocks in the scheduler. Because then it's also as if somebody says, like, I don't like your scheduler, they can just exchange it with something else. Counter. So these are like the meta information if you want to, for example, monitor buffers or something like this. Genau.
Excuse me, Ralph. Is there in the schedulers that we currently have, is there conditionally enableable?
Yes.
Yeah. Okay.
This is this example is from the present scheduler.
Thanks.
So it's the output where you can say, like, the base in it, then you have a base none, which is the major loop, and then you have different subparts, different functions running on different threads that are executed. This is thread safe. Make the code. I don't want to go into code data because it's just like 1,000 lines of code. The main thing is we use the same circular buffer technology that we use for the buffers, write down these events in there, and then at the end you read it out. And it's basically, the main work is generate this JSON file that is readable by Google Trace, but the format is very simple. But we thought it is useful because it's also used in other parts. So this is just to motivate it. Sometimes you have, for Google tracing, what you do there. I think this is, okay, there's a block signature. I have to, okay, this, maybe, do I need this? No, I think I can skip that. It's not important. Maybe just highlight, because it came up yesterday, is how do we name variables? Normally the names are directly derived from compile time, how you spell them out here. But if you say, like, I don't like them and I want to have some Chinese characters or UTF or snowmans, then you can give also alternate names and annotate them both in what the type is, what the name is that should be shown in the UI. Then you can also add your documentation automatically, where it's like, what is the intention of this variable name? So this is basically a replacement with Doxygen. And for microcontrollers, you can say, like, please throw away, this compiles away to nothing, and then it will be just a std string of the name. But this is like inbuilt. It's a bit wrong topic. Yeah, one of the pain points, and that you all probably all recognized and aware, is the compile time of GNU Radio 4. Initially, we had like one block which compiled maybe in 1 or 2 minutes. That's fine. Now we're heading over to a block library of 600 blocks, so having 600 times 2 minutes becomes painful. Or you can just select, if you're paid anyway, you can tell your boss, okay, I have to slack off, sorry, my computer is too slow, and I need some break time to drink a coffee. So that's a legitimate reason to slack off. I tried that, and my boss started to ask Alex, can you buy Ralph a faster computer, because maybe I wasn't working enough. But we all want to have a quicker response. If we develop something, we don't want to, none of us wants to wait for 6 minutes until we get an answer whether it worked or not. And sometimes it's not clear why it takes so much time to compile, but there is a very nice, for here there's an example, and originally it was like 4 minutes to block, and then, but we target 20 seconds, so it was too long. So in terms of improving compile time performance, there's some low-hanging fruits. One is just like to optimize your build system, where you use CC cache, do incremental builds. Ninja makes a big difference, Clang makes a big difference, but also not using the standard linker. So this is like low-hanging fruit, don't have to read. And that brought down the compile times from 4 minutes to like 2. Something that is still annoying, which I think is a bug, which you can see if you compare the GCC 13, for example, against the Clang 18, you see that is nearly like a factor of 2 difference between GCC and Clang for the same runtime performance. And we have to investigate why and maybe send a bug report to both. To GCC, so like, please become as fast as LLVM. And to LLVM, we want to get this down to 20 seconds. There is no reason why it should take so much time to optimize.
What's the fuse LD equals LDD?
That it uses an alternative linker. This is like it's a faster linker that comes with LLVM.
Okay.
You have different parts. You have the compilation, you have the linking, and then the parallel build step. These are the low-hanging fruits. There's no risk. Just use them, which we put in the standard build system already in, so that is safe. But just so that people are aware of that.
1 hour time. I mean, when I was building the thing that there was in the message that Alex sent out, I noticed on my, few-year-old laptop, it builds in like 24 minutes. Nothing special. So I'm trying to figure out how come I get 24 minutes on this 3-year-old laptop, and you guys are seeing an hour. Am I not building the same code?
Yours faster, because we incorporated this, and we had like lots of other changes in between. So this is.
I'm the code that you put up that was like the whatever it's called, GNU Radio 4, and that was in the email, right? When I build that on this like not very fancy laptop, it takes me something like 24 minutes. And then of course I installed it native so I could use Ccache. So then if nothing changed, it was done. But just even running it in the container was on the order of. It has a bunch of memory in it. So it's got like 48 gig in it, which may be why I'm not dying. Okay, but it's not super fast. It's like some i7 from a while back.
I think one of the issues you mentioned, like memory, is a critical thing. Some people say like, oh, let's use all the cores. Some compilation units need 4 to 5 gigabytes, so sometimes you very quickly run out of per unit, per compilation unit. If you have more, 16, okay. So part of that bottleneck is in the permutation it has to compute because of the recursive stud variant use in PMT. We have to find a solution. Like any help is appreciated. I just wanted to show like how to identify this problem, because people say like, this is just a hearsay. You have to, the proof is in the pudding. I can at least show how we've identified that this is the problem.
So I compiled on a VM. I gave the VM 12 gigabytes of RAM, which I think is already more than an average PC that runs GNU Radio. And I'm stuck for hours just copying from the swap file or whatever, and the swap file is over 10 gigabytes. I think it's
But you do like
RAM.
reusing all cores. So you said you use Ninja, you don't limit the number of cores you use for compiling, because then you run out of RAM and you start swapping, and then basically all bets are off.
Yeah.
Don't try to do this -J64 unless you have 256 gigabyte. You will shoot yourself in the foot. That's the beauty of C++. It's the fastest language out there, but you also get those foot guns where you can very quickly harm yourself. So try it with a single core or 2 cores, see whether it sticks below your RAM. Because the GCC doesn't give you a warning, or the Clang doesn't give you a warning when it hits this limit. And that's something that I would like to explore, how to tell GCC, stop optimizing. It's not worth the runtime performance at the end, so stop making early break off. But I think on the machines over there's I think 7 minutes for one chain. Relatively fast for the whole project. But it's a pain point, and in order to diagnose this, we haven't known about this, and the question was also like, how do you find out why it's so slow? So you can instrument like, why does the GCC take so much time? And then we found that somebody earlier in 2019 had the same question. Why does my compiler spend so much time on compiling, and what are the different parts? And they added basically the same Google Trace format to Clang. So you just have to have -f time trace. And it basically spits out the individual steps it does in the 2 or 3 stage compiling process. Then he wrote also like a small post-processing tool, Clang Build Analyzer, which boils down and gives you the hotspots for what is expensive. It's a free and open source tool developed by Aras Panchevicius. I'm not sure how to pronounce it. And it's already in Clang since Clang 9. And uses the same infrastructure as the profiler that we have and produces. Now, this is not a runtime performance. It looks a bit like this, but it's the same tool. This was the original trace. And you can see here like 4 minutes and 16 seconds for one particular build that we had. And that was for me like gold. Because you see like this, the total compilation time, you have the time. You see that's the front end and the back end. And you can see, for example, instantiation that takes time, how many how much time do you take for parsing the header files, how much you take time for instantiating the templates, and later code optimization. So I dug down here in this lower depth and thought like, what are the most expensive things? And was along, and then I found like, oh, std visit, lambda. And then you get also like directly the point where it's invoked, in the QA settings in this case, and I dug down. And yeah, variant, again, visit is expensive. And you get information on functions that took longest to compile this. So this is, for me at least, was gold. And function sets that took the longest to compile. And then you can identify, say like, can I simplify that code? Is it really necessary? And in my case, maybe I skip a bit. Wait a moment, you can, expensive headers to include. So obviously block, because it's a large one, but it's not that much actually, because it's just like 1 second that you need. So for parsing all GNU Radio 4.0 string files, it's just a second, so I didn't continue there. It's not worthwhile to use modules, for example, because modules will not improve much in 1 second. You have a bit of configuration. What I recommend for templated code to increase the max name length to 200, so to get a bit more meaningful template names, because they can get large. And yeah, I found this. What is the problem with this code? I mean, it works. What you reckon what is the problem with this code? So you have like this inside the settings interface, where basically you have here, you get a member, you get a field, a member field of the struct, and you check whether it matches the name, the key that you want to set from the PMT value, and whether you can write it for the given type that the field expects. So basically, if you have a string that is called context, which has been sent as settings, and you go through the runtime iteration, you say like, can I write a string to the field context? Is it possible or not? In this case, if it's violated, I want to throw out an exception. And what it does, because of you have different variant, you have different types, you have basically instantiate the error message for each possible type that is there. So what the compiler tried to do is like, oh, that must be very important code. I want to produce with the FMT format the best possible string generation that there is for each of the error message that I have. So if I have an exception that it will not last 10 milliseconds, but only a few hundred microseconds, it's like, thank you for your effort. I don't care. If I ever have this is a programming error that should not occur. I don't care whether it's 100 microseconds or milliseconds or even a second. I mean, even this error, if this will have to force to crash the program anyway. So I said like, let's try to outsmart the compiler a bit and say like, okay, let's simplify this so that it doesn't try to make a fancy printout, but just one that is enough to diagnose and say like, okay, here's the problem. And that got from, you saw before, 4 minutes. This one line of code chain got it down to 2 minutes. So low-hanging fruit. Still, 2 minutes. For me, we wanted to be below 20 seconds. So we had a poll, how fast do we want to have blocks to compile? Depending on the age, the younger ones amongst our team said like, no, 10 seconds and faster. And the older ones said like, 40, 50 seconds, so we agreed on the middle and said like, okay, that's our target, 20 seconds, somewhere in between. So, this is basically the commit that helped a lot. to half basically the compilation time. And we flattened the tuple iteration and also did some further enhancement. So the next step was going down to, okay, after these performance improvements, we got it down to 1 minute, which is better. Still, you have to think about it, this is like 1 minute times 600, so still a lot. I mean, like if you just have a small project, it's like 1 minute perfect, you don't care. But we want to eventually be able to compile the whole blocklib over and over again. Yeah, that brought it down now to the present stage. So I can't go too much into detail because that's a bit more practical example, but have a look at it. For the tooling, it's free for everybody to use. And if you find some other hotspots or some ways how to optimize certain codes, that would be highly appreciated if you do some pull requests and say like, okay, I can simplify this templating code structures. And this is a nice tool to identify where the bottlenecks are. And if you look, okay, didn't put it out, but some of the traces that I placed out, we believe that we fixed everything that is in the GNU Radio 4 code base. And now the remaining bottlenecks are largely in external libraries that we pull in, like FMT is very compile time heavy. Unfortunately, also the PMT is compile time heavy, not because it's well designed, but the thing is the recursive variant has a certain O2, O3, O4 complexity, and we have to think about like how can we break it down that at a certain recursion depth that it breaks off and just say like please provide some runtime code with a simple runtime for loop. Now the nice thing. Format. There's also, once I dig a bit deeper, once I start playing around with Clang, there is an X-ray toolkit, like X-ray instrument. This has the same features, but it's basically a runtime performance analyzer, which produces again the same JSON output format, which you can also use for profiling and then do your flame charts. I know there are other tools out there, but the nice thing about this, streamline integration, same format. You can always use the Google Trace format, and that's also easy to transmit between people and to compare. Okay, this is like an example. I put also on the website some demo files where you can play with, which are a bit more detailed, like Matthias did, where you can try out and see the pros cons when you enable certain parts of the code and disable. Yeah. It's on the Indico side. Now to the last part, which I think is a topic that I would like to address. This is more like an open discussion. There have been recently an increased discussion about cybersecurity, IT. There was a White House release in terms of what type of software requirements are put onto software that is used in critical infrastructure, and also guidelines that should be followed. In the US, it's the White House white paper together with the NSA. But I thought like, okay, the US is a forefront, but then I went back and I actually realized that Europe has already released this policy 2 years earlier, but everybody ignored it. But now they tightened the screw since last December and said like, eventually, both the European Commission, but also Germany, in our case Germany, the national government funding agencies will reduce funding for code that is not safe and doesn't conform to this basic cybersecurity acts. So we all want GNU Radio to be used and to be useful, and but there are certain opportunities, but there are also challenges and risks, and we have to think about like proper software engineering designs and be mindful of the total cost of ownership, because the larger the code base becomes, the more there's a risk of maintenance costs, but also challenges with respect to flexibility, onboarding, and adapting new changes. Because if you have a code base that takes 200,000 lines of code and you ask a new code developer, please make a change, it's very, I mean, like having a code base of 10,000 lines of code, it takes you like a couple of days, maybe a week to get into and modify it. If you have a code base that is 100,000, it's close to the limit that a single developer can't handle this anymore. And if it's too large, people will just swim on top and just to be able to do patchwork. And I think for GNU Radio 4, it's important that we focus on what has to be actually in the code, in the core, keep it clean, lean, and both from a maintenance point of view, so to ease the core developers' burden, but also that helps to make the code safer, because if you have a large code base, you accumulate technical debt, and you will unavoidably accumulate non-compliances. And that basically means that in the end you have a code base where it's not yet strictly enforced, but where government agencies rightfully, I think, will enforce it like, okay, we can't sponsor projects that don't have basic cybersecurity hygiene factors built in. And yeah, we should address that. And I think one of the possible mitigation strategies open for discussion is that we have to focus continuously on writing lean and clean code. Clean, not necessarily capitalized version, but clean in the sense of just the minimum that is absolutely needed. Follow open standards, that in particular if they already comply with certain securities. Not being shy on continuously iterating on the implementation and modifying it. That's the reason why we now try to nail down with GNU Radio 4 first a good user level API, where we think the user level API is okay, but then the other ones we should still work on the specific implementation to make sure that that it's rock solid. And yeah, but we also have to develop a way how to share this experience, both in terms of how we use C++, how we develop code within GNU Radio 4, and build up competencies. So, because we need more people. I mean, like now we're happy to further support GNU Radio 4 because we also use it in our facility. But GNU Radio is a community project, so it can't be if there's a critical bug, we can't be always there to immediately do a 24/7 hour fix. So there need to be more volunteers, but also I think other partners that invest into the same ecosystem that have also like an operational stake into using it to help each others out. I'm like, we're happy to continue contributing it, but I feel we cannot and we should not be the only ones. GNU Radio is not fair. We use fair, we want to contribute, but we have to widen, strengthen the community. And this, yeah, bus factor is important. So what did we do in GNU Radio 4? What are the thumb screws and the torturing implements that we put up? I hope is basically we added a lot of warnings. And these warnings are basically, let's say, the minimum reasonable set, which prevent most of the insecure coding habits. And depending on GCC or Clang, if you violate one of these warnings, they give you already, that's another reason to use GCC 14 or Clang 18, like a newer compiler, because the error message that you get during compile time are much more cleaner, nicer to understand. So if you see a warning, don't take it lightly and say like, come on, ignore it. This creates obfuscation. If you see a warning, fix it, because if it's in a larger project, you get the same warning hundreds of times, and eventually the compiler output will actually suppress some critical warnings which are in the realm of between warning and actually a bug. So let's keep all our code base clean, follow these warnings, because eventually we want to be able to move also to a strict any warning is an error, so any warning will cause the CI pipeline to fail, to make sure that we never accumulate too much technical debt or errors. And there the unit tests are important, because the unit tests explore different aspects of the API and cover most but not all of the ground of making the code secure. There's some additional ones for GCC, like misleading indentation, duplication, and so on. So there are certain things that both share, certain GCC. Now it's in between mix. Some error messages are cleaner in Clang, some better in GCC. What we do typically in-house is we alternate that. A couple of weeks we predominantly do GCC and then do we Clang. And that helps us also to make sure that they're on par, that we don't fall into the trap of a compiler bug, or that we exploit a compiler feature which is not conforming to the standard. So I would also invite you, this is not like GCC or Clang is better, use both, because both have merit. Yeah, and the key takeaways is like, try to catch issues early, don't ignore these. Try be proactive and fix them early on. So what we deploy additionally, you can have a look on the CI/CD pipeline. We use Sonalint, which is a free static code analysis. Clang Tidy and CPP check also well, but we found that Sonalint combines a lot of other checks, and they're also well integrated into GitHub, so you get a more meaningful explanation also why the code is bad. So if you use it, your IDE integration, it says like, that's fishy, and that's always it's a good place when it's not like your code is bad. But the nice thing of these tools, they say like, it's bad because of, and then they give like a small excerpt, often from the CPP core guidelines actually, where they say like, please don't use this because of this reason. You can continue reading. This is bad practice, but do this instead. Some compilers like Rust, they have it immediately as a compiler output, and also GCC and Clang do this as well. But these linters go one step further. They can also look at larger structures where you have unsafe or not so clean coding habits. And we provided default definitions for these. This is for compile time. Then during runtime, there are certain things that you can't catch during compile time, like if you have a dynamic structure out of bounds reach. And for this, there are compiler flags for the address sanitizer, the undefined behavior sanitizer, and threat sanitizers. The address sanitizer basically detects memory errors like buffer overflows or use after free. This is like how you can use it in a standalone context. The same for the threat sanitizers. Be careful. This is one of the reasons why the compile time goes up, because they heavily instrument the standard library code and put like wrappers around certain functions and enable debugging informations, and that explodes the combinatorics. That's one of the reasons why the compile time is long. But you can disable them if you say like, I really don't care, but I would, for production build, when you push it to GitHub, switch them back on, make a check on your local machine, because these check problems earlier. And latest in the CI will fail if you don't have them enabled and there's an underlying bug. Yeah, and in the undefined behavior sanitizers, there are a lot of structures that already detects that you shouldn't do. And they're also continuously updated, so they improve over time. So this is for us a very useful tool. Once you passed all of these, it doesn't mean that your code is error-free, but there was a talk by Herb Sutter, How to Make C++ Safer, and he showed that with many of these things, that 90% of the CVEs that are reported can be eliminated. It doesn't mean that everything is error-free, but the last 10% are often bugs that are not language-specific, but algorithm and implementation-specific, where the user is responsible for example, how you handle passwords, hashing, and this type of things. But that's basically the easiest hygiene factors that we should follow.
Ralph, just a question. Can you just flip back one? I can see the static analysis all the time, but when do you run the runtime? Do you run the runtime analysis, which has some overhead, right? I'm trying to understand, when do you use the runtime analysis? Because what I thought I heard you say is there's a consequence to performance if I turn these all on.
For the threat sanitizers particularly. For the address sanitizers, you add a bit of if-else. There's like, in most cases, the overhead is like 5–10%. What we do is we enable the address sanitizers and the UB sanitizers because they're fairly cheap, and then run the whole unit test suite and the profilers and the benchmarks with that. I know the benchmarks is not the fastest that you could have in the production use, but at least we know that under a reasonable use of our API, that within this run that is tested, it's done. What we want to do as well, which is not, it's more an accounting issue, but we want to also deploy more code coverage. In code coverage, there's like two ways how to do code coverage, just like to stupidly walk every if-else branch just to have everything green. The idea is we want to make meaningful unit tests, not to get the code coverage up, but as a meta information, code coverage is a good indication on which part of the code is actually being executed or being used at all, and if it's not, then it's a candidate, remove it. Or write a unit test that makes a meaningful use of that case. It's not always trivial, because especially for hardware, certain hardware failures is hard to simulate or to test in unit tests, but if we can reach a code coverage of, let's say, 90% for non-hardware blocks, or 95%, then that would be a good goal, and then means that we more confidently can say we're safe. And that's also part of the security audits. If you want to ever start a security audits, The steps are, what are our dependencies? Are they audited? What is our code base? How do we test it? How do we ensure that how do we deal with CVEs and how do we mitigate it? And these strategies, outlining and specifying them is part of, not the only step, but the first step. But we should be looking actively for help. I mean, like, there are some other users. I think Oak Ridge is also working on these topics, and other DOE and NSF-funded labs, where maybe we should ask for support. Can you help us making this safer? Also documentation, because that is useful also for the industry. Because when they say, like, I use GNU Radio and it's a vetted dependency, it's easier. They don't have to spin up their legal department. That saves them money, and that is an easier investment. So if we share this, then that's a real benefit for industry, for everybody involved.
One more question on that. So in the CI, if I just say make in the CI, see on GitHub, do I get all this stuff turned on and then?
Not the thread sanitizer.
Okay, not the thread. Okay, and all right.
But we could enable it, but the problem is.
And technically, which build type is this in CMake? Is this a
debug?
Okay, and with
the debug, I mean, like, there is.
And you've fiddled with the default, so it's not on -00 in the debug build?
Yeah, they're in. I mean, like, basically, these are just the CMake flags for the build. By default, the address sanitizer is on, UB sanitizer, I think UB sanitizer as well, but thread sanitizer is off. They're by default enabled for debug. And for release, they're disabled, because their release is more for performance.
Okay.
But that's also when we look for CI, when we merge something, even if there's some different behaviors on the CI for release than on local machines, but when we merge something, ultimately, okay, it has to be also compiled locally, but ultimately, even if the release fails on GitHub, we merge it if we know that it passes the debug builds for GCC, Clang, and Mscripten. But yeah, we want to have all of the tests work reliably, but there's some, especially the perf counter, for some bizarre reason. My feeling is that the GitHub runners are somehow castrated in terms of what they pass through, and for the kernel perf counters. We can't reproduce it locally, unfortunately, and we don't have enough diagnostics why it fails on the CI. Because even if we use the same runner, the same build system locally, it works. So it must be the host running machine that does some behind the scene, outside of the runner, that we don't catch. Yeah, secure coding practice. Please mind the compiler warnings. Treat them as errors to enforce code quality. Also leverage static analysis. Continuously check your code for issues, both in the IDE and CI. So don't just compile with the command line tool. I mean, that's also possible, but that's the level where an IDE is really useful. And use the runtime sanitizers, because if they flare up, they show you very early on, oh, there's a problem. And then one should stop, fix, and move on. Yeah, and combined with the code coverage, this covers a large fraction of possible CVEs. So security is an ongoing process. Never you say, like, my code base is secure now, but we have to regularly use these tools and improve upon this. And yeah, collaborate and automate. I mean, we're trying to automate already quite a bit, but it's also that all team members, everybody who contributes to GNU Radio, is aware that ideally they should check it. They should not use GitHub as a compiler to check whether their code compiles or not. They should ideally first compile it locally, because GNU Radio is an open source project, and unless we get extra funding from GitHub, the runners are scheduled and have a certain job limit per day. And if we have more people contributing to that, that can become a limiting factor. So test it early, not to stress the CI too much. Last but not least, this is not to annoy you. It's not like it's like, come on, you should. I hate you, and I want to make your life programming difficult or inconvenient. This is a bit difference between, for example, Rust and C++. By Rust, you're getting annoyed by default, and then you basically, and Rust educates you to say like, no, you shouldn't do this. This is unsafe. But early on, from the very first line of code you write, and say like, no, the borrow checker makes sure like, no, you don't want that. And then people take it are more accepting. So like, okay, sorry, I'm new into Rust. Thank you. I take up your comment. Yeah, exactly. And only once you know like, oh, I want to access hardware, they say, now use unsafe. And then it's like once you're at the level of using unsafe, you're already in the realm as a Rust developer in the realm where you say like, I have enough experience. I know now what it implies not following all the rules that I had to learn before. The problem is C++ is older. That has basically being open by default. And you have to add this additional checks as a hindsight. So many people say like, why do I have to put it? If I disable the warning, everything works fine. Only when my code only breaks when I put the warning in. And people not start thinking like, oh, you used a practice that was unsafe in the first place. So but this is a highly debated topic. I mean, like, Matthias can probably talk about hours about this, how to implement this which policy. C++ choose being very lenient and backwards compatible because you don't want to annoy people who use code bases from the 1960s. And now we have to think about how to move on. And my proposal, what we did also in the existing CI is we added these checks, not to annoy people, but when they contribute that they get early on a feedback and say like, hey, you can do better. And hopefully with these tools, that will be also meaningful to say why it fails. Okay, this is like some generic tricks. Again, just to wrap up. If you want to have distributed real-time programming tips, you want to improve the performance, first look always on the big O notation. Every computation that you don't have to do in the first place because of an algorithmic trick that you use is best. The best computation is the one that you don't have to do. So, and then have a look on how your computer works. Use const.expr and notably SIMD instructions. Keep your code simple. That's the next step, and the rest is like already quite detailed. But I think the two first ones are the most important one. And then some reference and some good reads. And let's discuss.